Suppose we have two sets, set A and the set B. Now each of the two sets have got 5 elements. Now set A has got the elements Aragorn, Gimli, Legolas, Boromir and Theoden. These are 5 characters from the Lord of the Rings. And B also has got 5 names. We have Arathorn the second, Glóin, Thranduil, Denethor the second and Thangol. Now here we have the total number of elements in the set A that's equals to 5. And the total number of elements in the set B that's equals to 5 as well. Now if we take the Cartesian product of the set A and B, how many ordered pairs we will get? Because we know the Cartesian product of A and B is going to give us ordered pair. So the total number of elements in the Cartesian product of A and B, that's going to be defined as take the total number of elements in the first set and multiply it to the total number of elements in the second set. So that means we will be having 5 times 5, that will be equals to 25 ordered pairs. So let's list all the ordered pairs when we take the Cartesian product of A and B. So here we have a total of 25 ordered pairs. So if we look at the first ordered pair, we have within braces, we have Aragorn, Arathorn the second. That means what we have done here is we have taken the first element of the set A and we have formed an ordered pair with the first element of the second set, that is B. Each of the elements in the each of the first elements in the ordered pair, the first elements being here we have Aragorn, next we also have Aragorn. If we take any random ordered pair, the first element is always going to belong to the set A and the second element is going to belong to the set B. Fine. Now we have found out the Cartesian product of A and B. However, what we'll do, we're going to pick up some special ordered pairs from this list. So out of the 25 ordered pairs, we have picked up 5 ordered pairs and we are calling this new set as the set represented by R. So here we have the first ordered pair where we have the first element as Aragorn and the second element as Arathorn the second. Next ordered pair consists of the first element which is Gimli and the second element that's Glóin. Then we have Legolas and Thranduil. We have Boromir, then Denethor the second, and we have Theoden and Thangol. Now this is a special type of set. Now if we consider R, let's say what we have R is a set, we'll try to write it in the set builder form. So the set is going to contain what? It's going to contain only ordered pair. So let's call the ordered pair as A, B, such that we have A belonging to the first set. That means whatever element that we pick up A, that's going to be an element from the first set A. Okay, and then B, the second element in the ordered pair, that's going to belong to the second set which is B. And clearly there's a relationship between these two elements A and B. So here we have A is the son of B. That is the relationship that we can see here, because Aragorn is the son of Arathorn the second, Gimli son of Glóin, we have Legolas son of Thranduil, Boromir son of Denethor the second, and Theoden king, the son of King Thangol. So here what we have done here is we have taken first the Cartesian product of set A and B, and from this set we have picked up some special ordered pairs, and these ordered pairs have been picked up in such a way such that the first element is related to the second element, and clearly we see here that this R, the set R, is going to be a subset of the set, the Cartesian product of A and B. Now when we can write in this fashion, this R is now going to have a special name. R is a relation. So what we are talking about here is a relationship, and R, it is a relation from the set A to B. It's going a relation that is being connecting the elements of set A with the elements of set B. Which means that if we consider the first order pair Aragorn, so we have Aragorn is related to Arathorn the second, because Aragorn is son of Arathorn the second. What we can write here is Aragorn R, Arathorn the second, Arathorn the second. This R signifies that we have a relation going from element of set A to the element of set B. Similarly, we can write Gimli R Glóin. So that would mean that we have Gimli related to Glóin, going from Gimli to Glóin. That means Gimli is the son of Glóin. Then we have Legolas. We have Legolas R Thranduil. So Thranduil, that means we have Legolas is the son of Thranduil. But however, if we know that Gimli is not the son of Tangle, Gimli is not the son of Tangle, so what we will do here, we'll simply write Gimli R Tangle. So Gimli R Tangle, but since Gimli is not son of Tangle, what we'll do, we will cross R, signifying that Gimli is not related to Tangle. So this is true for Boromir not being related to Gloin. That simply tells us that Gimli is not the son of Gloin. So this is how we can relate one element of an ordered pair with another element of that same ordered pair. So this is what is referred to as a relation. So let's go to the formal definition of a relation. So let's say we have two sets A and B, and these are two non-empty sets. Then a relation R going from A to B is such that it is a subset of the Cartesian product of the set A and B. That means R is going to be a relation from A to B. If the ordered pair A comma B belongs to the set R, where R is a relation, then we say that A is related to B, and we simply write it as ARB. It's very important what comes first, since we are taking the ordered pair with A coming first and B coming next. So while we write ARB, so A must lie to the left of R, the symbol R, and B must lie to the right of the symbol R. And if we have the ordered pair not belonging to the relation, the set, then A is not going to be related to B, and we simply write it as A not R, B. For instance, let us consider a set A. So let's say we have set A containing three elements, 1, 2, and 3. And then we have another set B. B contains the element A, B, and C. And let's say we have considered another set R, which is a set containing ordered pairs 1, comma B. Next we have 2, comma C. Next we have 1, comma A, and we have one more ordered pair being 3, comma A. Now clearly R is going to be a relationship from A to B. It's a relation going from A to B. That's because we have the first ordered pair 1, comma B. Clearly this is going to belong to R, and 1, comma B is also a member of the Cartesian product of A and B. It's, in other words, we can say that R is a subset of the Cartesian product of A and B. But we need to verify that all the elements of the relation is also a member of the Cartesian product of A and B. So here we can see 2, comma C, that belongs to the relation, and we have that same ordered pair 2, comma C also belonging to the Cartesian product of A and B. Similarly, we have the next element 1, comma A. But if we consider another ordered pair 2, comma B. Now clearly 2, comma B does not belong to the set R. Although 2, comma B belongs to the, while 2, comma B belongs to the Cartesian product of A and B, clearly in this case we can say that since 2, comma B does not belong to the relationship R, so we will simply write it as 2, not R, B, meaning that 2 is not related to B. Fine. Now that we have defined what relations are, let's talk about the total number of relations that are possible. So we'll again consider two non-empty sets A and B, each of them containing M and N elements respectively. Total number of elements in the set A, that's given as M, and the total number of elements in the second set, which is B, that's given as N. That means the total of N elements present. Now A, the Cartesian product of A and B, has got Mn ordered pairs. We have already established that fact. The total number of elements in the Cartesian product of A and B, that's equals to Mn. Now the question is, what is the total number of subsets of A and B? So that means what we have to find out is the total number of elements in the power set of A and B. We know that the total number of subsets in the power set of A and B, that's simply given by 2 raised to the power of Mn. This is from our definition of the set theory. So this is also going to be the total number of relations that's possible from A to B. So that means if we have two elements in the set A, let's call them A, comma B, and then we have a B. Let's say it also contains two elements, 1, comma 2. Okay, now total number of elements in the set A, total number of elements in the set A, that's equals to 2, and the total number of elements in the set B, that's equals to 2 as well. which means the total number of elements, and the Cartesian product of A and B, that's going to be equals to 2 times 2, which is 4. And we know, so when we write down the Cartesian product of A and B, so we'll get 4 ordered pairs. We have A comma 1, we have A comma 2. Next we have B comma 1, and we have B comma 2. Right. So how many subsets are possible? Since there are 4 elements, so that means there will be a total of 2 raised to the power of 4, which is going to be 16. So there will be a total of 16 subsets of the set, the Cartesian product of A and B. And also the maximum relations that can be made available from the Cartesian product is also going to be 16, because we know that R is a subset of the set A, the Cartesian product of A and B. So if A and B has a total of 16 subsets, that would mean that the relation R, which is a subset of this the Cartesian product of A and B, it's also going to have a maximum of 16 relations. That means, or we can say 16 ordered pairs where the first element is going to be related to the second element. Fine. And if we have a null set, if we have a null relationship phi, that means the ordered pairs, the first element and the second element has no relationship between them, none of the elements have any relationship between them, then we say it's a void relation. And we have the universal relation A and B, because the Cartesian product of A and B lists out all the ordered pairs. That's why it's referred to as the universal relation. These are going to be trivial relations from A to B. So here we have 2 sets A and B. We have to justify which of the following are relations going from A to B. Okay, now we have A consisting of 4 elements, A, B, C, and D. B also has got 4 elements, P, Q, R, and S. Okay, now what we'll do, we can find out the Cartesian product of A and B. So there will be a total of 4 times 4, 16 ordered pairs. So let's list all of them. So we have A comma B. All we have done is, first what we'll do, we're going to consider the first element of the set A, since we're taking a Cartesian product from A to B. So it's very important that we choose the element from A first, and then using the help of this element, we're going to form an ordered pair with each of the 4 elements of set B. So we're going to get A comma P, A comma Q. Next we have A comma R, followed by A comma S. Similarly, we repeat this pattern. We're going to consider the second element of the first set, which is B, and we're going to form an ordered pair with each of the 4 elements of B. So we have B comma P, we have B comma Q, then we have B comma R, followed by B comma S. Next we have C comma P, we have C comma Q, we have C comma R, and then we have C comma S. And finally we have D comma P, we have D comma Q, next we have D comma R, and then we have D comma S. So we have a total of 16 ordered pairs formed by taking the Cartesian product of A and B. Now coming to the first relation, R1. So here, in order to verify whether if R1 is a relation going from A to B, we have to check that each of these 3 elements, these 3 ordered pairs, A comma P, B comma R, and C comma S, also belongs to A and B or not. So here, if we consider the first element A comma P, yes, that belongs to the Cartesian product of A and B. What about B comma R, the ordered pair B comma R, that is also present. Then we have C comma S. So C comma S, yes, that's also present as well. So here we can say that R1 is clearly a subset of the set A and B, the Cartesian product of A and B. So that means R1 is indeed a relationship. What about R2? So here we have Q comma B. Is there any element Q comma B present in the Cartesian product of A and B? Nope. So we don't have to worry about the other ordered pair, since one of the element, which is the ordered pair Q comma B, that does not belong to the Cartesian product of A and B. This simply tells us that R2, this is not going to be a relation from A to B. Coming to R3, so we have A comma P, we have A comma P, we have A comma Q, so those are present. Then we have D comma P, that's present as well. We have C comma R and B comma R, C comma R, and we have B comma R, that's also present. So all the elements of the relation R3 are also a member of the Cartesian product of A and B. So clearly here we have R3 being a subset of A and B, the Cartesian product of A and B, meaning R3 is going to be a relationship. Then we come to the last relationship R form. So you have A comma P that belongs to the Cartesian product of A and B. However, Q comma A, this particular ordered pair, this is not a member of the Cartesian product of A and B, which means we can simply say that R4 is not a subset of the Cartesian product of A and B, and since it's not a subset, then R4 is not going to be a relation from A to B. Next, we will talk about some definitions of the domain, range, and codomain of a relation. So let's say we have a set A which contains, this is a non-empty but a finite set. We have a set A, let's say, containing two elements A comma B. Next, we have another non-empty finite set B containing the elements 1 and 2. Now next, after this, after we have defined the two sets A and B, we're going to take the Cartesian product of the sets A and B. So here they will get an ordered pair. So we'll be getting four ordered pairs: A comma 1, A comma 2. We have B comma 1 and B comma 2. So that is the Cartesian product of the set A and B. Now what we will do, from this set we're going to pick up only two elements. Let's say we pick up A comma 1 and B comma 2. Now clearly the set R is going to be a subset of the set, the Cartesian product of A and B. That's because whatever elements we have chosen in R, the relation R, we have picked it up from the Cartesian product of A and B. So definitely R is going to be a relation going from A to B. Now the question is, what is the domain of this relation R? So domain means what we will do, we're going to consider the first element of the ordered pair of, since we have two ordered pairs here, so we're going to consider from each of the two ordered pairs the first element. So here we have the element A and the element B. So what we will say that the domain of the relation R, that is going to be equals to, this is going to simply be numbers, the element A and B. So it's going to be a set containing two elements A and B. Next, what about the range? Now the range will be, the range of R will be such that we're going to now pick up only the second elements of each of the two ordered pairs. So here we have 1 and 2. So that means the range of R is going to be the set containing the elements 1 and 2. That's a very simple task of how we can find out the domain and the range of a given relation. Then there is another third concept, which is the codomain of R. So codomain of R is simply going to be the set B. Set B is going to be defined as the codomain of R. So here we have the codomain of the set R. This is simply going to be the set B, and set B here contains the elements 1 and 2. Fine. Now in this particular case, here we observe that the codomain of the relation R is exactly the same as the range of that same relation R. So here let's consider an example. We have A and B, two non-zero finite sets, and R is a relation going from A to B, which is defined as the set containing three ordered pairs 1, 8, 3, 6, and 5, 2. Now we need to do is determine the domain and the range of this R, the relation R. That's a very simple task. So the domain of the relation R, that is simply going to be the first element of each of the three ordered pairs. So the first elements are 1, 3, and 5. Our domain is going to be 1, 3, and 5. And then we need to find out the range. The range of the relation R, that's going to be the second element of each of the three ordered pairs. So those are 8, 6, and 2. We have 8, 6, and 2. As you can observe here, domain of R, all these three elements belong to the set A. 1, 3, and 5 belong to the set A, and the elements present in the range of the relation R, those are present in the set B. So we have 8, 6, and 2. Okay, let's move on to the next problem. Problem number 3. So we have two sets A and B. A and B has got both 4 elements. So our goal will be to find out the domain and range of the relation R, where we have the relation R going from A to B. It's defined as the ordered pair X, Y belonging to the relationship R, if and only if X is greater than Y. Okay, so it's a very simple task. We know the step will be, so we are given here two sets A and B. So A has got the elements 1, 3, 5, and 7. And we have the set B containing the elements 2, 4, 6, and 8. Now, quick question. What will be the total number of elements if we take the Cartesian product of A and B? Clearly, since we have 4 elements in A and 4 elements in B, so there will be a total of 16 ordered pairs. We're not going to list all the ordered pairs. So here we'll straight away move on and find out the relation R. Because here the relation R is a subset of the ordered pair, a subset of the Cartesian product of A and B. So that means we are the relation R is also going to have some ordered pair. The ordered pair is given by x comma y with the condition that x must be greater than y. So that means whatever elements that we pick up from the set A, because x belongs to the first set A, it's given here, it's from A to B, it's not from B to A. So A is, as our relationship goes from A to B and we have an ordered pair given by x comma y, so we must immediately understand that x must belong to the set A and y must belong to the set B. Now we are going to pick up some elements from set A such that this element is going to be greater than all the elements present in the set B. So here we cannot pick up the element 1 because 1 is actually less than 2, 4, 6 and 8. So we are going to skip 1. We'll straight away move to the next element, which is 3. Is 3 less than any of the elements in B? Definitely it's less than 2. So we're going to form our first ordered pair 3 comma 2. That's the only ordered pair possible if we consider the element 3 from the set A. Moving on, we are going to take the third element from set A, which is 5. We know, so we can observe that 5 is less than the element 2 in set B. 5 is less than the element 4 in the set B. And then we were going to consider the element 7 from the first set. So here 7 is less than 2, 7 is less than 4, and then we have 7 is greater than 2, 7 is greater than 4, and then we have 7 being greater than 6. Okay, so these are all the ordered pairs that belong to the relation R going from A to B. Now that we have the relation, what is our next task? Our next task will be to obtain the domain and range of R. That's now an extremely simple task. So domain of R is going to be the first element of each of the ordered pair. So we have 3, 5 and 7. Right. We have so this is now 7 greater than 6. This simply means that we have 7 comma 6. We have 7 comma 6. So the domain of R will be 3, 5 and 7, and then we have the range of the relation R. So that's going to be equals to the second element of the relation R, or second element of each of the ordered pairs. So we have 2, 4, 2, 4, 6. So that means it's going to be simply 2, 4 and 6. So that's going to be the range of the relation R. Moving on. Next we have two sets A and B. A has 3 elements, 2, 4 and 5. B has got a total of 6 elements. We have 1, 2, 3, 4, 6 and 8. These are the two non-zero finite sets, and R is a relation going from A to B, which is defined as x R y. That means x is related to y if and only if x divides y. So that means we have a relation between the element x and the element y, which is given by x dividing y. Okay, let's try to understand the problem. So we have the set A containing 2, 4 and 5. B has got the 6 elements, 1, 2, 3, 4, 6 and 8. So here if we consider 2, now clearly we have the relation R going from A to B. This is a relation going from A to B. So that means if we take the ordered pair x comma y, clearly x must belong to the set A and y must belong to the second set, that is B here. So if we take an element 2 from the first set A, so we have to find out a corresponding element y from that B such that 2 divides that element in the set B. So if we can say 2R2, this is a relationship. That's a true relation because 2 divides 2. Next we can take 2R4 because 2 divides 4 as well. Then we have 2R6, 2 divides 6. And next we have 2R8, meaning 2 divides 8. Okay, next what we'll do, we're going to take the second element from the first set A, which is 4. Now 4 does not divide 1. 4 does not divide 2, but 4 divides straight away 1. So we have 4R4, that's a true relationship. And then we have 4R8. 4 divides 8. And then finally if we consider 5, now 5 is not going to divide any of the elements from the set B, so there is no relation. So here we can write that 5 is not related to any of the elements. I'm considering one example here. 5 is not related to 1, meaning 5 is not dividing 1 here. So now that we have the relationship, what we can do is we can specify the ordered pair of the relation R. So that's simply going to be, so in place of 2R2 we can say 2 comma 2. 2R4 means we have 2 comma 2R6 means we have 2 comma 6. 2R8 means we have 2 comma 8. Then we have next ordered pair 4 comma 4, and the last one which is 4 comma 8. So this is going to be the relation R. Now that we have the relation R, we can easily define its domain. So the domain is going to be the first element of each of the ordered pairs. So we have 2 2 2, 4 and 4. So that means there are two elements, 2 and 4. We don't have to repeat the elements. Next we have the range of the relation R. So that's going to be the second element of each of the ordered pairs. So we have 2 4 6 8. 4 and 8 are repeating, so we have 2 4 6 and 8. So that's going to be the range of the relation R. Fine. So here we're going to discuss a very important definition, which is the inverse relation. Suppose we have two non-empty sets A and B, and we have a relation R going from A to B. If we want to take the inverse of the same relation R, it is going to be denoted by R inverse, and it's a relation going from B to A, and is defined as such that we have R inverse equals to the set containing the ordered pairs B comma A, such that the ordered pair A comma B belonging to R. In simple terms, we have that if we have the ordered pair A comma B belonging to R, this is going to be true if and only if we interchange the position of the elements in the ordered pair. That means A becomes B and B becomes A. That is going to be an ordered pair which is going to belong to the inverse of the relations R. And what we can say here is that domain of the relation R is simply going to be equals to the inverse, the range of the inverse relation R, and the range of R is going to be equals to the domain of the inverse of the relation R. This can be best understood by taking an example. Let's do one numerical. So here we have two sets A and B. So A contains the elements 1, 2 and 3. B has got 4 elements A, B, C and D. These are both two non-zero finite sets. And we have a relation R going from A to B, which is defined as the set containing 4 ordered pairs 1 comma A, 1 comma C, 2 comma D and 2 comma C. We need to determine the inverse of the relation R as well as the domain and range. Okay, let us begin. So we start by considering the original relation R, which is the set of the ordered pairs 1 comma A, 1 comma C, we have 2 comma D, and we have 2 comma C. Fine. Now we need to find out the inverse relation R. So what is the definition? Let's quickly recall. The inverse relation of R is simply the set containing the ordered pairs B comma A, such that we have A comma B belonging to the relation R. That means taking the help of the ordered pairs present in the original relation R, all we have to do is interchange the position of A and B, which means our first ordered pair, which is 1 comma A in case of R, is going to now become A comma 1. Then 1 comma C is simply going to be C comma 1. 2 comma D becomes D comma 2, and 2 comma C becomes C comma 2. So this is the inverse relation R. Now that we have the inverse relation R, we can immediately obtain its domain and range. So the domain of the inverse relation R, all we have to do is take the first element of each of the 4 ordered pairs. So here we have A, C, D and C. C is repeating twice, but we'll only consider once. So we have A comma C comma D. So that's going to be the domain of the inverse relation R. Now we can also find out the range. The range of the inverse relation R is going to be the second element of the ordered pairs. So we have 1, 1, 2, 2, which means we have the range given by 1 comma 2. Now here we can observe, if we consider the original relation R, what is the domain of R? The domain of R is going to be the elements that the first element of each of the ordered pair. So here we observe that's 1 comma 2. So we have the domain of R exactly the same as range of the inverse relation R. And then if we want to find out its range, so range is going to be A, C and D. So A, C, D, that's going to be the range of R, which means that it's exactly the same as the domain of the inverse relation R.